Hello, this is Dr. Muhammad, and this is another video for dynamics of structures. And I'm going to talk today about the equation of motion for single degree of freedom system. And the main contents of this video is going to be related to the degree of freedom, the definition of it. Actually, I should have explained it last video, but because of the time limitation, I couldn't. So today I'm going to talk about it, and I'm going to explain and define the meaning of degree of freedom. And then we are going to derive the equation of motion for the single degree of freedom system using three different ways. The first one is using Newton's second law, and the second is using D'Alembert's principle, and the third is using a spring-damper system. Okay, now let's start with the meaning of the definition of the degree of freedom. So for the degree of freedom, for short, I would put it like this, the DOF, which is the degree of freedom of the system. We need to have a kind of definition for it first. So we can say that the degrees of freedom of an engineering system are the number of independent coordinates necessary or required, let's put it like required to establish the position of its particle at any time. So let's go through this again. So it's the degrees of freedom of an engineering system are the number of independent coordinates. This is number one that we need to highlight here. Independent coordinates, okay, required to establish the position of its particle at any time. This is the key, another key. So this means that whenever we have a system, for example, like a single story building system like this, whenever that we want to highlight or to describe the position of any particle, let's assume that this point here, which is the mass of the system, we want to assume that we have a coordinate that is going to be used to describe the position of this particle at any time. So we have here, this is the displacement, and we are applying f of t. So we are interested in this mass to describe its motion in this horizontal direction or axis, which is, for example, that is going to give us the displacement y at any point. We are not interested in the vertical axis or any inclined axis. So we are not interested in this axis or this axis or this axis, right? We are interested in the horizontal. So this one is going to be, we call it single degree of freedom, SDF. This is single degree of freedom means that there is one coordinate only is required or necessary or needed in order to describe the position of this particle or this mass at any time. We're talking about time here. Well, what if that we have another system, but it is having multi-stories? We have multi-masses here. This means that our system needs multiple axes in order to describe the motion of its system, the particles and the masses of the system, right? So in this case, we are going to call this multi-degree of freedom, MDF, multi-degree of freedom system. Okay? If another case that we have, and this case is related to a system that is requiring infinite number of coordinates, if we have masses here, and this mass is infinite number of masses, okay, and particles. So we need like different types of coordinates or axes to describe the position of the particle, this particle, these particles, which is the masses distributed here, at each point of time. So we are going to call this infinite degree of freedom system. So we have single degree of freedom system where that we are interested only in one axis or one level of the mass, and we can describe the particle of the mass or this particle at any time. And we have multi-degree freedom system when there is like a number of degrees of freedom that we know them well, and we can describe them in a number. But if we have infinite number of degrees of freedom or infinite number of axes required for describing the particle, in this case we are going to say or describe this system as infinite degree of freedom system. Okay? So now today we are going to derive the equation of motion for single degree of freedom system, SDF. Okay, now let's jump to the equation of motion. So we're going to call it EOM, which means that equation of motion for, we're going to call this SDOF from now on, single degree of freedom system. Single degree of freedom system. Okay, now let's go, and first we are going to use the first approach. So we're going to use Newton's second law, which is Newton's second law, okay, is going to be our main approach for describing the equation of motion of the single degree freedom system. So we need first to remember the Newton's second law. So I'm going to define it here. It is, I know that you know it well. So if we want to define this, we can say that it is the rate, or the definition, we can say that it is the rate of change of momentum. The rate of change of momentum of any mass particle, of any mass particle, of any mass particle, we are going to designate it with M, is equal to the net force, take care of this word, net force, acting on it. So now let's highlight the important things here in this definition. The rate of change, the word rate implies that there is time is involved here. So time is involved here. The rate of change of momentum. So rate means that T is going to be used. Momentum means that M times V, we're going to use it, of any mass. We're talking, of course, about mass. Mass particle M is equal to the net. Take care of this word. It is the net force acting on it. The net force acting on it. So the total force, it is, as we said, the total force or the net force, because maybe we are having different forces in different directions. This means that we need to take care of this, that we are dealing with the net force. We are dealing with the net force. Okay. Now let's go and derive from this definition the meaning or let's put the first equation for us. Okay, so first of all, the net force here, net force, the net force is going to equal the rate of change of momentum. The rate of change means that d by dt. As I said, time is involved. This means that we need to use it in our mathematical model. So the rate means that we have change with time. With what? M, which is momentum. It is m times v. V, it is going to be the rate of change of displacement, du by dt, right? So the velocity is going to be defined as du by dt, right? So we have m and du by dt, and all of them, we are going to get the rate of change of it. So we need to differentiate with respect to t. Okay, so now this means that it is going to equal, if we say that this m is going to be constant, if we assume that this m is constant, commonly it is constant. In this case, we are going to say that m, put it outside, it is going to be d squared u over dt squared. The second derivative of displacement with time, which means it equals to m times u double dot, u double dot. So what is the meaning of u double dot here? So if we are talking about mass that is going to move, okay? So if we have a mass, okay, this is the mass, okay? Again, without any illustration, because we are using only the Newton's second law. From the definition, we are going to derive our equation. So I didn't use any like illustrations here or any sketch even, because this is going to be used in our third way for deriving the equation of motion. So this mass, whenever it moves with acceleration, then in this case, we are going to find that if we apply some force on it, this means that let's assume that this force is changing with time. So in this case, we are going to say that this net force is going to be external force applied. If we have external force, let's assume it, we call it P of t. P, it is the force. T means that it is changing with time, okay? And the system is going to develop some resistance of this force. We call it elastic resistance force or inelastic. So we call it the elastic, okay? Or sometimes it is inelastic, but later on I'm going to talk about the inelastic. Elastic resistance force, okay? And we are going to call this to be Fs. So let's assume that P of t is applied in this direction. F of s, it is resistance force. It is going to be developed in this direction, which is opposite to it. And we have something else, which is the damping. We call it damping resistance force. Damping resistance force. And by default, we are expecting this damping to be developed in the opposite direction of the motion. And we are going to denote it by Fd. So let's circle these things. We have P of t, and its direction is, as you can see, we have Fs, which is elastic resistance force, and this is its direction. And we have the damping force, which is going to be also resisting the motion, and it is, as you can see here, it is related to the resistance, means that the opposite direction. Okay? Okay. That's very clear and simple up till now. Let's go to the next phase and deriving the equation, let's use the same word here. So if we say that we have our system, so we have our system here, which is, let's assume that we are making a cut in the system. Okay, we have a mass here, this is mass, and we have system that is having damping. So we are having damping here. So as we said, it is like dashpot system. Okay. Okay. And let's assume that this is here, this is FD, which is the damping that is going to take place. Okay. And let's assume that the force that is being applied, changing with time, is P of T. And the system is going to develop elastic forces that is going to be developed, which is Fs here. Sorry, let's make this small lowercase, okay, Fd. So based on this, we can put from the equilibrium equation, we can say that P of T, which is applied to the right, minus the resisting force from, or the damping force, minus this damping force, as we said, it is opposite to the system. So we have, it is in this direction, okay? Opposite to the motion of the system, okay? So we have, let's assume that we have the elastic force that is coming from the system itself, from the columns, for example. So this is why I put two arrows here. But actually both of them, they are going to represent the elastic resistant force. And we have damping force, which is coming from, do you remember the structure damping? We said that many sources of damping, the material and the friction for the steel structures, or opening and closing of cracks and so on. Okay? So P of T minus F of D minus F of S, the elastic force, okay, equals to what? If this P of T is dynamic force, means that our system is going to be in motion, right? So this means that, let's go to Newton's second law. Yes, here, the right-hand side is going to be, so the net force here is going to be these three things, three components, and the right-hand side is going to be M dot U double dot. So we have M times U double dot. Again, in order not to lose what we were talking about. P of T, it is the dynamic force that is being applied. Dynamic force. F of D, it is damping force, right? From where, as we mentioned before, for structure damping. F of S, it is resistance force, the elastic resistance force. Okay, resistance force coming from the system itself. The elastic resistance force comes from what? Exactly, also from the material, from the dimension of the system, from the cross-section of the components, and from the boundary conditions. So now we have this equation, which is the second law of Newton already taken. Then we are going to rearrange it in a form. So we're going to say that our system is going, we are going to put, rearrange it and put it the right-hand side to be in the left-hand side and vice versa. So we are going to say that M U double dot, okay, plus F of D plus F of S equals to the external dynamic load that is being applied. Okay, so this is going to be our equation of motion. This is going to be our equation of motion. Remember well, F of D, do you remember that we have mentioned before about this, and we said that F of D is related to what? Exactly, to the velocity. See the coefficient, damping coefficient times the velocity of the mass. And this F of S, it is related to what? Do you remember? Exactly, in the elastic systems, you can recall and visit the previous video, and you are going to find that the elastic force is related to the stiffness of the system times u. It is related to u, the displacement. Okay? So now we can put our equation of motion to be, the final equation of motion is going to be like mu double dot plus c u dot plus k u equals to the external applied force, which is P of T. Okay, so this is K times U. Actually, the elastic force, only I want to highlight something here. It is sidetrack of what really want to highlight, but sidetrack. Sometimes the elastic force is function actually in U and U dot. Okay, it is function. If we're talking about, it's not elastic force, I mean if it's, we're talking about any elastic force is going to be applied here. So it is going to be related to U and U double dot. But again, it's a sidetrack, forgot about it now because we're going to talk about elastic system for the time being. Okay, so this is our equation of motion. This is our equation of motion. Okay, so now this is the equation of motion. This is the equation of motion for SDOF using Newton's second law. Newton's second law. Okay, now let's go to another variance or another variation of this equation of motion. It's going to give us the same output, but using different approach, which is highly appealed by engineers. So let's go here and say the second, put it using D'Alembert's. So they use it or call it like this, D'Alembert's principle or approach. Okay, what we are going to do here. Actually, this this system or this principle is, it appeals to structure students. Attractive, this is, we can say that it is attractive to structural engineers and students and so on. They like it very much because it is easy for them to understand, and the concept is easy to be grasped. So here the main idea, we can put here the main idea, we can call it the static equilibrium concept. Static equilibrium concept. This is why it appeals to the students or structural engineers and students, because we are using static equilibrium concepts. So it is easy for us to understand. The point is, or the main idea here is that if we have a system and we have the mass, as we said before, okay, so in this system we are going to have resistance based on different, let's use other color here. So we are going to have F of D, right? And we are going to apply, if we say that we are going to apply in the beginning external dynamic force, P of T, then the system is going to develop damping force, and it is going to develop elastic resistance force. Okay, this is by default, we are going to assume that. And we are going to assume something that is fictitious. We call it the fictitious inertia force. Okay, so we're going to use another thing here. There is, whenever there is dynamic loading is applied on a mass, this mass is going to resist this force or dynamic load by something called inertia force, as I have explained in the first video, F inertia. And this F inertia, we know that it equals to M times U double dot. It is related to the acceleration of the system. Okay, so this means that this is static equilibrium equation for us. So we can put here another thing, which is it is based on fictitious inertia force. It is based on fictitious inertia force. This means that we are putting this fictitious inertia. We know well, whenever the mass is going to move in this direction, there must be opposite resistance coming from the inertia. Okay? So based on this, simply we are going to put our equation. Let's put our equation in different color. So our equation is going to be, that is summation of f in the direction of y, where it's horizontal direction. For example, if we say this is, for example, x, this is x, and this is y. So summation of, let's assume it is x here, summation of fx equal to 0. Okay, so this means that simply, so at each time, right? Because we are talking about different time. This force that is being applied here is going to be applied, and it is going to be changing with time, right? So this means that f of x is going to be 0. We want to maintain equilibrium every time at each time, right? So this means that going to this, we are having p of t, right, minus f of d minus f of s equals to, or let's assume minus here again, mu double dot, right, equal to 0. So we have summed all the forces in the x direction. P of t, the dynamic or the applied outside dynamic loading. F of d, it is the damping that is going to be developed by the system to resist the motion, and the elastic resistance that is going to be developed also by the system to resist the motion. And we found that there is something else, which is the inertia force that is going to be developed by the mass to maintain its equilibrium, or to maintain or to restore its original position, as we know. So this would equal to 0 in order to obtain the equilibrium. Based on this, we can put it again, our final, we are going to rearrange it. We're going to find that mu double dot, as we have done before, c u dot plus k u equals to p of t. So here, this is the system equation of motion, which is the same as we have obtained from here, right? So here we are having now, this is the equation of motion for our SDOF. Okay, this is the equation of motion for our SDOF. Okay, this is using D'Alembert's principle. This is using D'Alembert's principle. Okay. Now let's go to the next. Now let's talk about the last approach that we are going to use, which is using the mass spring damper system. Mass spring damper system. This is what we are going to use. We can say this is the classical way found in mechanical vibration and elementary physics textbooks. What you are going to see now, it is the elementary one, or this is the classical way found in mechanical vibration. You can write this. This is the classical way found in mechanical vibration and elementary physics, okay? Physics textbooks. Okay, so simply what we are going to do here is, by default, you're going to find it very easy actually, because we are going to find that we have a system. Let's assume that we have a system here. Okay, and so that we are having a trolley, for example, here, and there is no friction. This means that it is on wheels here, and it is connected to the wall here with a spring and connected also with a dashpot. Okay, so actually here what is happening is that we are assuming a system. This system, it has a mass, and we apply force on this system, dynamic force, which is P of t. And when we apply this force on the system, we found that if we are going to study the free body diagram of this system, okay, the free body diagram of the system, this is the mass that is being there, okay? So we found that the forces that is going to be developed is, first we apply the dynamic load which is applied from the outside. There is resisting elastic force that is going to be developed due to the spring stiffness and due to the damping of the dashpot. So we're going to have here F of S, and we are going to have here the F of D, right? And the mass is always going to develop forces in the opposite direction of the motion. So if we say that the motion is going to be in this direction, this means that our mass is going to develop a kind of inertia force opposite to this. So it is going to be in the opposite direction. So we call this FBD, free body diagram, free body diagram of the system. Free body diagram of the system. So from here we can also put the same equation of motion. It's very easy for us now. We can put it like, as we said before, it is P of t minus F of S minus F of D, okay, minus the inertia forces, okay, would equal to 0. After rearrangement, you are going to find that our equation of motion is mu double dot plus c u dot plus k u equals to plus ku equals to the external force P of t. And this is our equation of motion. This is our equation of motion. So again, we ended with our equation of motion for single degree of freedom system. For single degree of freedom system. Okay? So now these are the different ways. So these are the different ways for obtaining the equation of motion. I think that it is pretty straightforward for us now to understand, to recall what I have said in this and recap what I have explained in this video. First of all, I mentioned about the meaning of the degree of freedom here, and then after that I mentioned about the equation of motion of single degree freedom system, and we said that we have three different ways for them. We have three different ways for representing the equation of motion. The first one is going to be the Newton's second law, and we found that from the bare definition of the equation, or from the definition of Newton's second law, which is the rate of change of momentum of any mass particle m is equal to the net force acting on it. From this definition we could derive our equation, and we could end with the equation of motion. After deriving the equations, then we found that we can end with the equation of motion, which is always giving us the inertia term which is implying or having the u double dot, the acceleration, and then we have the coefficient, displacement coefficient, the damping coefficient times the velocity of the mass plus the stiffness coefficient or the stiffness of the system times u, which is going to be the displacement. And we said that the resistance of the system, whether it is elastic or inelastic, it depends on u if we are talking about the elastic system, and if we are talking about inelastic system, it is going to depend on u and u dot. Okay, and the right hand side is the applied force, the damping, the dynamic force that is being applied in the system, and based on which we obtain the equation of motion for our single degree of freedom system. Another principle that commonly used, which we call it the D'Alembert's principle. So we said that it's attractive for structural engineering students, and the main idea implies the static equilibrium concept. This is why the students like it and the structural engineers, because we are talking about static equilibrium. And it is based on something we call it fictitious inertia force. The idea is whenever that we have a mass and it is under motion, then there is fictitious or there is inertia forces going to be developed opposite to the direction of motion. So if we apply a force P of t that is going to make this mass move in this direction, then the inertia force is going to be developed and it is going to be resisting this applied force or dynamic force. And it's going to be here, Fi is going to be opposite to the direction of the motion. And we found that this system is going to develop damping force, as we said, from the sources of damping, like structure damping and so on, if we're talking about structure. And we are going to find that there is elastic resistance that is going to be conducted or induced as well. Okay? And we said the sources of this elastic resistance. It is based on the dimension of the structure, the boundary conditions, and the material and the components also. Okay? So when we put all of them together, then we are going to take the equation of motion to be the static equilibrium equation, f of x equals 0. As you can see, we have all of these forces with their directions. This means that if we put them in one equation, we can obtain the same equation that we have obtained using Newton's second law. Okay? So this is the equation of motion using single degree of freedom system. And then for the single degree of freedom system, and here the last one was the mass spring damper system, and we said that you can find it in the classical, this is the classical way that is going to be found in mechanical, vibration, and elementary physics textbooks. Simply we put a trolley like this and we put the mass, we apply the external loading P of t and connect this mass with the fixed wall with the spring and dashpot. The spring has a stiffness K, the dashpot has a coefficient C, and when we use the free body diagram concept, we can put the forces applied on the system as P of t external dynamic load being applied and acts to the right, and we are going to find that the forces that is going to be developed is going to resist this dynamic force, which is the elastic force and the damping force, and the mass is going to develop inertia forces, which is m dot u double dot. Then putting it in an equation, we are going to find that equation of motion for single degree of freedom system is going to be obtained. This is the end of this video, and I hope that we have an idea of how to get and obtain the equation of motion for single degree of freedom system. Okay, thank you and see you in the next video.